everyone, and welcome back to another video provided by SVSU's Online Tutoring. My name is Joel, and today we'll be finishing off with section 9.1, exponential functions, and we'll end it with talking about the application behind compounded interest. So, before we talk about this little text blurb over here in this example, what I want to do is go through a quick derivation for formula 1 over here. So say for instance that I have some amount of money, my principal investment P, that I want to invest, right? And after 1 year it gets compounded by the annual interest rate R. And so the final amount that I end up with is represented by A, which is equal to P plus P times R. Or you could simply say P times 1 plus R. And this is true for the first year, okay? Or 1 year. So after 1 year, it's compounded by 1 plus R, okay? But what if I did a second year? So if I did a second year, then what happens is that I multiply my first year with this 1 plus R term again. So I have A, which is equal to P times 1 plus R times 1 plus R. And this would be the final balance amount after 2 years. And if I wanted to do 3 years, it would be A equal to P times 1 plus R times 1 plus R times 1 plus R. And hopefully you see the pattern here. So this is 3 years. And the pattern is that if I continue on with this and I do it for some unknown amount of years, I'll have my final amount A equal to P times 1 plus R raised to the T power. And so this is T years. But this formula here is only good for compounding annually, and that's not always what happens. Sometimes you have compoundings where you do it quarterly or monthly or semi-annually or continuously, and if you're doing it for the first three, all except for continuous, then the R value here gets divided by n, which if we go up here to our little key, n is the number of compounding per year. And n can take the values of 1, in which case if it's 1 we end up with the same equation that we have here. It can end up, so yeah, that's annual. N can be 2, which is semi-annual. N can be equal to 4, which is quarterly. And n can end up being equal to 12, which is monthly. And so it's important to keep that in mind. The wording for these compounded interest problems usually give you this information right from the start, and so you know exactly what your end value should be. So if we're compounding for anything other than annual or continuous, then our equation becomes A equal to P times 1 plus R divided by n raised to the n times t. So we have successfully derived the first formula in our little text blurb right here, okay? Which is n compoundings per year, okay? So let's take a look at an example. Let's say that we invested a amount of $15,000 at an annual interest rate of 6.5%. And we want to know what the balance is after 10 years if it's compounded quarterly. So all we do is that we take equation 1, which is written in green. So we have A equal to P times 1 plus R divided by N raised to the NT. And we just want to substitute our values. So P is equal to that 15,000. So we have 15,000 times 1 plus R, which is 6.5%, but we have to convert that to a decimal. So 6.5% divided by 100% gives us a decimal of 0.065. So we have 0.065 divided by 4, because we're compounding quarterly, raised to 4 times 10, where the 10 comes from the amount of money after 10 years. And so when we throw that into a calculator, we end up with a money value of 28,583.38. But let's say instead we wanted to compound monthly. And so in this scenario, n is equal to 12. So we go through and we do the exact same substitution, except now n is equal to 12. So we have 0.065 divided by 12 raised to the 12 times 10. And once we do that, we end up with an amount of 28,682.76 cents. And finally, to compare all these values, what if we compounded continuously? So when we compound continuously, we're no longer using the first formula. Instead, we have a base of E right here raised to the R times T. So it's raised to the annual interest rate times the amount of time. And the reason for that, you'll see in a second here. So if we go through and do that math, so we have A equal to that 15,000 times E raised to the 0.065 times 10, and we end up with a final amount of 28,733.11. And so if you notice, the continuous amount is greater than both the monthly compounded and the quarterly compounded. And the reason behind this is that when we compound continuously, it's essentially like a limit on the amount of money that we'll end up with. And so you can verify this with having n be equal to 100, 1,000, 10,000, or even up to 100,000. Obviously, if we keep increasing n, so if n were to equal like 10 billion, so let's see, 100,000, million, billion. If n were to be like 10 billion, then it would probably begin to approach or even surpass this number, but there's no way you're going to be compounding your money or you're not going to be compounding it 10 billion times. And that's just because it's not practical in the real world. So when we do a continuous compounding, it's more about the limit that we will end up with after n being very, very large, but not too large. Just like up to the 100,000 range there. Okay, that's the end of this topic. It's a lot to cover, but doing more examples and being more familiar with the keywords here will help out a lot in learning this. Alright, see you next time.